Yep.
All right. Welcome, everyone. This session of SLE is Software Language Design and Implementation 2. My name is Jeff Smits. I'll be the session chair. The first talk that we have is Type Checking with Rewriting Rules by Dimi Racordon.
Yep. Thank you very much. Okay, hello everyone. I'm Dimi. I'm a postdoc researcher at EPFL, and I work on programming language design and implementation. Today I will be talking in part about an implementation strategy for programming languages that are based on type classes. I will be giving my talk in the context of Hylo, which is a programming language that I've been developing in collaboration with people from the industry for about 2-3 years. Hylo is a programming language for high-level systems programming. It's designed to be fast by definition, so it has zero-cost abstraction. If you come from Rust or C++, this means like you can build complicated abstractions but without loss of efficiency. And the user can rely on optimization guarantees to make sure that everything runs fast. But today we will be talking about another aspect that Hylo is designed for, is its story for generics and generic programming. And this story is based on type classes, and that will be the focus of what I'm going to talk now. So a key part of Hylo's story for generic programming are traits. A trait describes a concept or a collection of requirements that are expressed in the form of types and operations that another type should provide. And if the type provides these different requirements, then it will conform to the trait. So here, for instance, I'm declaring a concept that is describing the well-known iterator pattern, and it has one associated type that describes the elements that are produced by the iterator, and it has an operation as a requirement that describes, well, the operation of the iterator itself. Now, the in-out specifier is part of Hylo's story for safety, for memory safety. It's a systems programming language, but we can ignore it today, at least for the purpose of this talk. You can just pretend that it doesn't exist. So we can use this trait to express generic algorithms. So here, for instance, we're looking at a generic fold operator that can operate on any data that does conform to iterator. So we have a constraint here that says that this thing will work on T. T can be any arbitrary type, but T must be an iterator. And that gives us the guarantee that axis.next here is an operation that is well-defined. And if you want to understand more about the benefits of this approach, well, come to see me later this week when I will be talking about that at Onwards essay. Now, we can provide conformance of a type to a trait retroactively, but we have to do it explicitly. So here, for instance, I'm declaring that uint64, which represents 64 bits inside integers, do conform to this iterator trait. I did not define this type myself. It's come from the standard library, but still I can extend the type to provide this additional conformance. And here I'm saying that these operate as buffers of 8 bytes, null-terminated buffer of 8 bytes. So we can mostly ignore the implementation. The point is that now, for the rest of my application, I can treat these 64-bit integers just like if they were iterators. So putting everything together, I can finally call my generic function without much ceremony. Here, for instance, I'm just calling fold edge. Well, I'm iterating over my buffer, which is represented by a integer. So one interesting of this system is we can easily combine the different algorithms, generic algorithms, and we can add constraints as necessary. For instance, I can write a sum operation that requires a generic parameter to be iterator, but additionally requires the element of these iterators to be numeric, and so I know now that the addition is defined. And similarly, I can write another generic function here, and that requires that the associated type of the iterator be exactly Boolean. So these two examples here show the two kinds of constraint that we can play with in Hylo. We have conformance constraint that requires a type to conform to a particular trait, and we have equality constraint that constrain a type to be equal to another type. another interesting aspect of this system is we can define recursive conformance constraints. So to illustrate, we can look at this trait, which defines the collection. This is actually extracted from Hylo standard library, and it comes with two associated types. The first represents the elements of the collection, just as we've seen before with iterator, and the second represents slices of the collection. You can think about slices of an array, for instance. And notice that the slice must be collection themselves, and this is a recursive conformance constraint because we are constraining the associated type to be satisfying the trait that introduces this associated type. We are also constraining the elements to be the same as the collection. That makes sense. If you are just a projection of an array, then your elements are the same as the base array. And we are also constraining the slice of a slice to be itself type. So the purpose of this last constraint is best understood if we think about monomorphization. I don't have much time to get into these details, but you can look at the paper to understand why we would need such a kind of constraint. So for the purpose of this talk, what's interesting is it's sufficient to observe that these last two constraints let us express expressions like that. So we know that T is a collection, and T has a slice. The slice of a slice is also a collection, and the slice of a slice is a slice. So T the slice, the slice, the slice, the slice is equal to just T the slice. And this is nice and fun. We can play with these kind of expressions, but it also makes type checking really hard. In fact, this problem was already formulated in 2008 by Tom Shrivers in the context of Haskell, and he dubbed that the entailment problem. The issue is that the signature of F here is describing a sort of theory, and under the theory, there are additional equalities that we can derive here. So for instance, now knowing that T is the element of T are conformant to numeric, we also know that the element of slices of T conform to numeric because of the equalities that we have defined everywhere. So this means that all of that is well typed. So the type equalities that are entailed by the set of constraints are not necessarily trivial. Here, in the previous example, it was fairly easy to understand, but in this example, should this program type check? I will not let you minate it. This is a fairly convoluted example. Actually, it should type check. And the question boils down to know whether TCB is equal to TA, and that happens to be true under the constraint that I've defined here. But first, fun fact, we can express this exact program in Rust, and Rust will say that it doesn't type check. It will say that these two types are unequal. So what gives? Well, the difficulty stems from the fact that when we add recursive constraints, then we create universally quantified formula. In particular, in this example, this constraint is equivalent to a universally quantified implication. So now that means that if we want to prove type equalities, we need to be a bit clever about the way we want to instantiate generic parameters. And, well, that's difficult. It's not just difficult. In fact, it's actually undecidable. And I will briefly demonstrate this claim, but I should mention that the proof was made by Slava Pestov first, who is an engineer at Apple, and he made the proof in the context of Swift, which is the language on which Hylo was originally designed. I will repeat here his proof in the context of Hylo, and the paper gives it in a more general context, in a more formal framework. So the proof is based on two observations. The first is that we can encode finitely presented free monoids into traits and constraints, and I will define these terms later. The second is that deciding type equality is like deciding the word problem, and the word problem is well established as an undecidable problem on finitely presented free monoids, and so that gives us undecidable type checking here. So going into the details, I think it's worth repeating some definitions for people like me who didn't pay enough attention during their algebra classes. And the first is free monoid. So if you have sigma, that's an alphabet, then a free monoid, it's a monoid defined with this alphabet, and the operation of the monoid is concatenation, and the identity is the empty string. Now we can use that to create a finitely presented free monoid, which can be thought as a kind of quotient of this free monoid, and this is a pair of a free monoid and a congruence, so a relation that says that different elements of the free monoid might be equal. Well, they are equal. It's just a free monoid with a relation. And then we have the monoid congruence, and then this is a lot of Greek salad, just to explain that, well, this is the set of all the terms of the free monoids that can be made equal, not only those that are directly inside the relation, but also those that could be obtained by adding prefixes and suffixes. Okay? So bear with me, we are almost done with the definitions, but first maybe an example. So here we can have a little fun example. If we take this finitely represented monoid, which consists of just the letter S, and a congruence that defines a relationship between SS and the empty string, well then actually we have encoded integers modulo 2. That is, if we just take the length of the strings, then the monoid congruence contains all the strings that have whose lengths are pair, and all the strings whose lengths are odds. These are part of the congruences. But perhaps more interestingly, if we go back to the previous example, we can know that what we asked before, so T, C, B, and TA are in the monoid congruence of this finitely presented free monoid. But I will come back to why we can make the equivalence here between the trait and between the finitely presented free monoid. So now that we have that, the last definition I want to introduce is the word problem, which consists of determining whether two terms of a finitely presented free monoid are equivalent. And it turns out that this problem is undecidable. It's actually well established. So if we can encode now these finitely presented free monoids into traits, then we will have proven that we have undecidable type checking. And that's exactly what we will do now. So in broad strokes, we can define the encoding that way. We can say that each letter of the monoid is an associative type constrained by the trait that introduces it. So an associative type with a recursive constraint, as we've seen with the collection and the element before. And then we'll say that every pair that is intercongruent is represented by an inequality constraint defined in the trait. So for instance, here, if we go back to our modulo 2 example, integers modulo 2 example, we have the single letter of the monoid, which is represented by this associative type. As you can see, it's also constrained recursively to be a Z2. And then the single element of the congruence is represented by an equality constraint. And to convince ourselves that our encoding makes sense, we can write this little function. And now we have a very expensive way to show that indeed modulo 2 is equal to 0. But if we have done this translation for this simple monoid, maybe we can do it for more interesting cases. And well, there you go. Here is a monoid with undecidable word problem. And so now we have undecidable type equality. It's undecidable to tell whether any arbitrary terms that we can form out of this trait are equal. So what now? Well, there are two ways to deal with undecidability in programming languages. This is not the end of the world. The first is to say that we can just add restrictions to the syntax to just rule out the cases that are undecidable. But this is not possible here because there are real concrete use cases that are necessary and that we want to represent in our language. One of them is the collection trait that I showed before. So we need to deal with this recursive conformance constraint. The next thing that we can do is that we can maybe run with some fuel, right? You try for some time, and then if you couldn't succeed, then you fail. And this is what Rust is doing, but this is a bit unsatisfactory because, well, then you get a false negative, and we don't like to have false negative. Another thing that you could do is that you could be a little more clever. You can reject more programs, but at least you can have a complete answer that doesn't just depend on fuel. And this is what Rust is. This is what Hylo is doing. The compiler, for instance, will not accept this trait at all, so you cannot just ask for an undecidable question, because as soon as you write this trait, the compiler will say, oh, sorry, this trait is too complex. And the message is intentionally not very specific. That's because for Hylo, there is no way to tell whether this is truly an undecidable signature or just a signature for which the compiler cannot build the system on the line. So this is better for user experience because now, at the very least, if my trait is accepted by the compiler, then I have the guarantee that every time I query the system for inequality, I will have a complete answer. It will be a yes or no, not a maybe or sorry, I tried and I failed because it took too long. So how do we get there? Well, the idea is roughly to reuse the translation that we just defined, just in the other way around. We want to express type checking as a reverting problem. And more precisely, there are two questions that we need to answer. Are two types equal? This is the obvious first question. And the other one is, does this type conform to a particular trait? This is the question that we will ask when we try to instantiate a generic parameter that has a constraint on it. So the first question has an obvious translation, right? We just encode the types into terms, then we rewrite the terms, and if they have the same normal form, then we're done. For the second question, we'll see that we need to work just a little more. So step one in the translation, we need to define an alphabet. So here we can define this thing. So we have, and the syntax here is chosen because it looks a little like Hylo. So the first thing is that we can say that C, a trait, belongs to the alphabet when we put it in the brackets. Then the second thing means a trait, a type seen as it's conformal to a trait belongs to the alphabet. I will show examples later. And then any arbitrary type belongs also to the alphabet. So any arbitrary type of Hylo int is part of the alphabet. So for instance, we can write now this term. This is a type followed by a selection of an associated type. So T is supposedly an associated type defined by the concept C, or the trait C, and then dot C. This term doesn't necessarily correspond to a type, it's just a term that we are allowed to write with this alphabet. Right? This will be the alphabet of our rewriting rules. The next thing that we need to do is to encode types into terms. So now we need to actually create terms that make sense. So here we have only two rules, very simple. The first is, so we define the encoding with this function phi. And the first thing that we do is we say that if tau is a selection of an associated type, so t.element, for instance, from before, then we take the translation of the t, and then we just append this this letter that means select a type, select an associated type, right? And then for any other type, we just reuse the same type as it is. We don't do anything. So t.element would become t dot square bracket c colon colon t. Oh, well, actually, this is the example I wanted to show. So yeah, we have given that t is an iterator, t.element is this term here that we have. Step 3, we need to define a term reduction order. This will become more obvious why we need to do that later. But here, we could do anything, right? We just want to have a ordering relation on the different terms. And we can pick the obvious thing. We can say, well, lexicographic order or whatever you want. This is not very important. There might have been some details here. You can look at the paper for why this specific term reduction order is nice. But for the purpose of this talk, any order would do. And then we need to create the rewriting rules. So there are two cases. For a conformance constraint, we will create a rule that is like that. We will just encode the term, the type into a term, and then we will append the protocol symbol, and then we will the trait symbol, and then we will say that this rewrites to the term encoded, so without the appendage. And for an equality constraint, we will say that one translation of a type rewrites to the other, and the order of the direction of the arrow depends on the term order relationship. So these are our rewriting rules. So for instance, we can encode our trait into this rewriting system. This is the integers modulo 2 that we had before. We have the first rule that says that self corresponds to the type that will eventually conform to this trait. It's a generic parameter that is implicit in the declaration of the trait. So self conforms to Z2. Then we have the first constraint that's selecting. Sorry, this is selecting s.s is conforming to Z2, and then we have the conformance constraint. So those are the constraints that are generated from this trait. So now what happens if we ask whether 5 is congruent to 3, or more precisely, what happens if we ask, does self.s.s.s is equal to self.s.s.s? Then we start with the type on the left, we encode this type, and then we use the last rule to rewrite it, and we eventually get to a normal form. Then we do the same thing for the terms on the right, and since they have the same normal form, then we can conclude that these things are equal. Okay, we win. What happens if we ask whether self.s.s does conform to Z2? Then in this case, we start with the term equivalent to the type suffixed by the trait, as the rule said. So we add this suffix. We rewrite this. We find a normal form. Then we do the same with the type without the suffix. And then we get, again, to the same normal form. So we can conclude that indeed self.s.s conform to Z2. And we win again. So we're very close. We're not there yet, because if we go back to our running example with the silly equality here, it will not work. Why? Because if we try to rewrite these things, there are actually no rules that apply, and so they don't have the same normal form, but we know for a fact that these things should be equal. So the problem is that our rewriting rules do not form a confluent rewriting system. And maybe to understand what we should do, we could try to prove this by ourselves. We can try to prove it by hand using the congruence that we have. So if we wanted to do that, we could probably come up with this sequence here. But we are humans, so we can do clever things. And crucially, the clever thing that we did here is to realize that we needed to make the term grow bigger before it could be smaller. This is the critical part of the proof, right? This is what requires some cleverness, and the compilers are dumb things, so they don't know how to do that, or they would just explore everything, and then we will have a very, very long type checking. So what we need is to find a way to teach this clever trick to the compiler. So crucially here, the trick is due to the fact that there are two ways to rewrite the term that we have on the top. First, we could rewrite CC, and then we would get just the B here by eliminating CC. This is what we get from the last constraint. Or we could rewrite CA. So this is called a critical pair if you have learned about rewriting systems. And fortunately, there is a nice procedure called the Knuth-Bendix completion procedure that can teach the compiler this kind of trick here that we can use to recognize critical pairs and then fix the critical pairs by adding rules. So specifically in this example, all we have to do is to say, well, to create a confluent system, we can just say that you can rewrite self.c.b directly to self.a, and then we're done. And this is fine, because everything was a congruence to begin with, so we are safe here. So we'll not get into all the details of the Knuth-Bendix completion. This is a well-known algorithm, and there are details in the paper. But, well, what we do is this kind of rewritings, and then we're done. So now, back to our example, to understand how things work, we still need to understand one last thing. I said before that recursive conformance constraints create universally quantified formulas. So where are the universal quantifiers in our rewriting rules? Well, there are two missing steps in the translation that I didn't give you. The first is that we need to remove the leading type for all rewriting rules that represent conformance constraints. So, for instance, we will get to this. And the next is that we need to replace the trait receiver by a trait symbol for those that are equality constraints. So just trust me on this. There are details in the paper if you want to understand why that works. But here, what we can know now is that this trick is basically encoding the universal quantification. Why? Because, well, let's add this function. This function has this constraint, so we will just add this new equivalent rule to the entire system. And now, because this rule overlaps with other rules by the completion procedure, we will just add a new rule in the system. So we will essentially instantiate the universal quantification for this for this specific type T here. So there is more in the paper. We can think about how to handle trait refinements. So for instance, if we say that a trait inherits from another trait, how to implement all of this efficiently, how do we optimize rewriting systems so that our type checkers are fast, and how we handle name resolution, which is another trick, another tricky thing to do, and all of these are defined in the paper. What I want to leave you with is that, well, recursive constraints and associated types have undecidable type equality, and this is not just a property of Hylo, it's a property of Swift, it's a property of Rust, and it's a property of Haskell. But we can encode queries to the type signatures into rewriting rules, and the completion gives us a semi-decidable type equality, which is better for the user experiment. And everything is implemented in Hylo, so please check out Hylo, and now I'm ready to take questions. Thank you very much for your attention.
All right. Who would like to start with a question? Nobody. All right. Well, maybe I'll start. You mentioned a couple of things that you didn't get around to. So one thing that I would be really interested in is to hear more about how you made this performant. Can you give us some small insight?
Yeah, sure. So this is a string rewriting system. So the difficult part is to find these critical pairs because you need to find overlaps between rules. And here we had very simple example, but you can imagine that if you make your signatures grow, then you will have dozens of rules. And you need to check basically all rules against all rules at all positions. So if you do it naively, it's an n cube thing, which is something we definitely don't want to have in a compiler. But fortunately, you can express that in a trie, so then a prefix tree. And so now you can have a very efficient search into a prefix tree that goes back to n squared in the worst case, but in many cases, you just give up the search fairly quickly because you realize that your terms don't match at all from the get-go, and so it's almost linear in practice.
And okay, so if it finds out that these things don't match very much, is that the point where you say this trait is too complex, or is that?
Oh no, so this is when we run the completion. So the completion is trying to find critical pairs and then add new rules to fix those critical pairs. Now those new rules need to be checked against all the other rules that you had before, and that might find new critical pairs and then add new rules to the system. So there is just a bound on the number of rules that I will add to the system until I conclude that the system is too complex. This is more like art than science because this is an undecidable problem, so there is no way to really detect that you are correct in saying that the system will not converge. But in my experience, trying to compile real programs, you can have fairly tight bounds because systems that really grow big are almost always undecidable.
Okay. Yes.
Yeah, so I had I guess a follow-up question. So if you choose the number of these bounds you can add, is that something that's sort of baked into the semantics of the language in a sense that you don't want your program to compile one day and not the next day because you updated the version of the compiler or whatever sort of random reasons, right? That tests that pass one day should still pass the next day. So
yeah, so this is a bit difficult.
Yeah, so that's my question, I guess. Are you going to pick a number and go like, that's the definition of?
Yeah, so I just picked the number. I picked 1,000 because it seems good enough. This is actually difficult to guarantee that it will compile in the future. I mean, the algorithm doesn't change, so probably it will. But if you add more, you could add one seemingly harmless constraint in the system, and that will break the system. So this is a little brittle in that sense. Yeah, that's clearly a weakness of the approach.
All right, let's thank the speaker again.
Thank you.